With question 1, I'm sure we can see that the first question, they wanted us to check if V is a vector space or not, and it was like 3 marks. So eventually the easiest way I could think of this is that this is not a vector space, because if it was, they were gonna give us 10 marks or something. So we should first inspect, right? We can see that this is cannot be a vector space and be given 3 marks. That's based on general knowledge, right? So what we are going to do first, so what we need to focus on is the structure. Whether it's a vector space or not, that one for now, it should not concern us. The first thing that we should look at is how we're going to get these marks, or how we're going to collect them. So what you're going to do first, you are always going to pick 2 elements from V. You say, right, as long as this is not the 1D space, you're going to pick, and these elements should be satisfying this. If it's a matrix, you're going to pick A and B. If it's a vector space, you're going to, if it's any those like this, right, you're going to pick U and V, right, if it was those. So what you're going to do now, we're going to let first A be an element of V, such that you can write it in words, right, which is fine. You say such that now, after having the such that, now you're going to copy this, equate it to A, then copy that again, equate it to B. On B, you're just gonna put primes, prime, right? So what I'm saying is this: you're going to say such that A is equals to A, B, C, D. You must copy everything. Don't leave anything else out, right? Everything should be satisfied, such that BC is equals to 0 and B is equals to A prime, C prime, that's B prime, D prime, such that B prime and C prime is equals to 0. You see, right? Now, what they're telling us is that every time we multiply these 2, we must get a 0. So every time you pick some elements here, you must make sure that one of them is 0. That's the only way you can multiply something and something you get a 0. It's if the other thing is 0, right? So this is the first structure. This is 1 mark, right? You get your mark. Then after this, we are going to first check closure under addition. You see, right? So when you are checking closure under addition, you need to write that now I'm checking closure under addition. I'm checking closure. You need to write here that this is closure under addition. You say, right? Then you say that A plus B is equals to A, B, C, D plus A prime, B prime. You don't just start with counterexample, guys. I realize that there are some people, they just come here and do a counterexample. You see, you must first start by writing the structures. This is a 1 mark. You get to 1 mark. Then you add these. Then you get to A plus A prime, B plus B prime, C plus C prime, D plus D prime. And they say that when we multiply the middle ones together, we must get a 0. So after here, we must come and say such that if I multiply C plus C prime with B plus B prime, this one is 1. I'm going to get a 0, but I'm not going to say it's equal to 0. I must prove that. So I must get, for this to be true, this must be 0, right? So let's prove if we're going to get 0. So we just simplify this. It's going to be C times B plus C times B prime. This is supposed to be B prime. Then plus C prime times B plus C prime times B prime. Now, we go back from what we have from the beginning. We know that B times C is equals to 0. B prime times C prime is equal to 0. So we know that this is going to be equal to, we get rid of this, this is 0, plus C B prime, plus C prime B, plus this is 0 also. You see, right? From our assumption. Now we get that we're only left with C B prime plus C prime B. But we don't know what this is, right? So what we need to do now, we need to come and look for a counterexample because we don't know what this is. The only way we can check, the moment you come across such a thing, let's say you get to this point like this, you must know that obviously there's something that is wrong here, or this thing might not hold. You say, right? So you're going to come here and come and say by counterexample. And the counterexample that you must choose, you must make sure that it disagrees with this question. You see, or you must make sure that it disproves. Remember what is the meaning, what is the main aim of a counterexample? It is to disprove. You see, right? It's to prove that something is not holding. So when we prove this, we're going to, we copy this entire thing. It's like I'm copying this. Let me show you so that you guys don't make counterexample. You're still gonna pick the same thing as this. Still gonna pick the same thing as this. Remember, this is another mark. You are looking for the last mark. So we let this is the meaning of a counterexample. You're still gonna have the same thing. Now the only difference is that these now are gonna be values. These now are gonna be values. So here we can take anything. We can even have 0, 0. We don't care about this. Then this one 1, then 0. So that when you multiply these, you get a 0. You say, right? 1 times 0, you get a 0. Then this will remain a 0. This is 1, this is 0. When you multiply 0 and 1, you get a 0. You say, right? Now, but when we add A plus B, we're going to get 0, 1, 1, 0. Such that when you multiply 1 and 1, we don't get a 0. You say, right? Therefore, this means that A plus B is not an element of V. Hence, closure does not hold, which follows that V is not a vector space. Then you get your last mark, right? So we have seen that V is not a vector space, right? Any question on this before we go to the next question? Any question on this?
I have a question.
Yeah.
Does it necessarily have to be, like the elements do it, does it necessarily have to be A, little A prime?
No, you can use you can use any A1, A2, X1, X2, you can still change them, it's fine.
Okay.
As long as the condition is satisfied that you were given, you say, right, this condition, then you're good to go.
Okay, thank you.
Yeah. So now we have 1.2, right? Now with 1.2, this is a proof that you were given. I think this is there on your notes, but we can I don't know, but I think discussing a proof like this, Ruby, I think, yeah, you have to focus. They send you the scope of the sub, which the proof theorems you're gonna have, of the theorems that you're going to have. I think if they did, then we can look at them at some point. For now, we can look at the other things. But here's what they expect you to do here, right? So they say let W1, W2 up until double N B subspaces of V. I can try to explain it, right? Then they say prove that the intersection of these subspaces is also a subspace of V. You see? So first of all, what they want us to prove. First of all, what they want us to prove is this. This is 1.2. And the question it says that we should let double 1 up until double n be a subspace of V, and then it said that we must prove the intersection, meaning that this is the intersection, n should be I from, since this starts from double 1, right? From double 1 up until double n, so this will just be double I. So this is the intersection. So the intersection of V. So now they want us to prove that this intersection of these subspaces, remember that these individually are subspaces, right? Double 1, double 2, and potential double n. They want us to prove that these intersections are also a subspace of, is the intersection of V. They're also subspace of V, right? So it means that what you need to prove, first thing, you need to prove closure under addition, meaning that you must come and let V, let's say you let V and U to be an element of this intersection. Right? Then after letting this be an element of this intersection, you must come and show that, or you can explain. You can really explain, right? And then I think what you can explain as is that let's say they say that these are, let me say this. Oh, they say that these individually subspaces of V, right? So we can come and say, since let's say we can just say since Wi is a subspace. Remember that these are subspaces. Wi is just this. So here I'm trying to summarize this, right? I don't want to write W1, W2. You must know this. This is Wi. Then this intersection is this. Okay. Yeah, that is the intersection. Yeah, then that is it. So since this, we know since this is a subspace of V, so that's what we can say first. We can say, since this is a subspace of V. So I think that since this is a subspace of V, then when you add the two subspaces, when you add the two subspaces, when you get, let's say W is a subspace, right? And then I take V, let's say V and U from those subspaces, then I add them. When I get a subspace, what is the addition of two subspaces? It's a subspace, right? Guys, isn't it that the addition of two subspaces is a subspace? Okay. Yeah, I expected you to be answering when I ask general knowledge, but it's fine. So we know that when we add the two subspaces, we're going to get a subspace, right? So we can just say for all I is let's say I can just say subspace. But since I've already said the subspace, I can just keep it like this. Just say for all I. And then this will be an element of this for all I. If I add them, then this hence means that. But you can try to use the one that you are given right there, right, in the guide. But what I'm trying to tell you here is that if they bring a question like this, what you're going to do, you're going to use what you're given. First, you let, this is the structure, you let two elements from those intersection, right? You let two elements from the intersection. So you let this be an element of that intersection. Then you show that the addition of those two elements will belong to Wi, since Wi is a subspace of V. It means that there is some addition of elements within that Wi. Then since this happens for all I, it means that also this will happen for the intersection. So if two elements are being taken from Wi, then we do an intersection of them, obviously it will still exist. You see, right? So that's the case in this one. Then the second thing that you can do, is to show that let's say there is a zero vex. This contains a zero vex. So you can just come and say that since, let's say, since each Wi, you see all the reasons are the same. It's always since Wi is a subspace. It's a subspace for all I. For all I. And then I think what we can say, we can just say that 0 will be an element of Wi. First, we must show that 0, if this Wi is a subspace, it means that it contains 0. And when I take the intersection of Wi, that 0 will still belong there. You say, right? Then I say, thus, the intersection, they're just there to confuse you. You must always know that if something belongs to this, it will also belong to its intersection. If it belongs to this, in this case of subspaces, it will also belong to its intersection. Then you just give the reason, since Wi is a subspace. Even this one, we said so. If something belongs to Wi, it will also belong to its intersection. You say, right? If something belongs to Wi, it will also belong to its intersection, as long as we're working with subspaces. Do you see that? It means that when you come to show the last one of a scalar multiplication, since we know that if we're going to take a scalar multiplication, then here I should have written 0 vector, right? 0 vector. So we know that here we need to pick some element from Wi. So we can let just one element. We can let V be an element of Wi. You say, right? Then we say that since the same reasoning, Wi is a subspace of V for all I. You say, right? So since that is a subspace for all I, then we pick this and we pick a scale. Let C be any scale. Then C U, oh, it was V, not U. This will be an element of Wi. So since CV is an element of Wi and Wi is a subspace, then indeed this will also be an element of its intersection. You see, right? So this will always be the case. If this belongs to Wi and Wi is a subspace, it doesn't matter how you put these words, you can try to put them anyhow. But as long as at the end you mention that Wi is a subspace of V for all I and this belongs to Wi, then it means that it also belongs to its intersection. You say, right? Then you say that therefore this is the intersection is a subspace of V. Right, so this one you can try to look at it, and then you look at the one in the guide, right? You try to see, I think if you fail to understand something, you can try to summarize it, right? Then it will be simple that way. And then any question? In any questions?
No question.
Or should we just move to 1.3, right?
Yes.
All right, so with 1.3, they said, let me see on this, they said what? W is equals to, they say is equals to f element of c ab such that the integral of abf of x dx is equals to 0. And so this is about all continuous functions on the closed interval ab. And they say determine if w is a subspace of v or not, right? So I think this could be, it can possibly be, looking at the marks. Let's just try. I think 3 marks can be for showing those 3 enzymes. Sometimes the marks can tell you what's happening. 3 marks can be for the enzymes, and then 2 marks for the conclusion, right? So I think it's possible that this might hold due to these marks. So let's go and check. It's W is equal to F, okay. And it's 1.3. This say W is equal to, I think it was F element of C continuous over the closed interval AB, then such that the integral, it spoke about the integral AB f of x dx, which should be equal to 0. Yeah, so now if we're told to check if this is a subspace of V or not, right? So what we are going to do here, first, remember this, the structure here. What you do first, you pick 2 elements from this, which they said it's equal to all this thing, you see, right? So we let, since here we're dealing with integrals, we can just let they say f element of c a b, we can just let f and g, because they already tell us we're dealing with f. And then we can just let f g be an element of w, such that this f belongs to some closed interval, some continuous function, which is, or this is an element which, or in other words, we are saying that this is a continuous function over a closed interval AB, such that if we take the integral of that function with respect to x, we are going to get a 0. Then we say, and now we have g being an element of, so that g is also continuous over this closed interval, such that the element of AB g of x dx is equal to 0. Then we add them. We are going to add f plus g. You see, right? But there is no need for us to even say f plus g, right? We can just take this, add this plus this. We can even do that. We can say f element of c a b. I can take it through this stage, right? Plus g element of c a b, such that, you see, both will bring their such that after that, then we're just going to take it from there. f of x dx plus integral of ab g of x dx. So we must get that at the end this must give us a 0. When we add these two, we must get a 0. And what do we know from here? We know that this is 0, the integral of f of x is 0, the integral of g of x is 0, meaning that at the end we are going to get a 0. Do we agree on this? And this will be f plus g c a b. We are also preserving the fact that this is continuous over the interval AB. So we're trying to show that also their addition will be preserved within that closed interval. You see, right? Then we are good with this. Now, we have seen that closure holds under addition. So we can deduce to say, therefore, closure under addition holds. You see, right? Then now we come and check the second one, which is 0. Want to check if there is a 0 vector. So we're going to let f element of that continuous function over the closed interval AB. Then we say such that the interval of AB f of x dx is equal to 0, and we just let some function also from its closed interval, and we can let e from that to be a continuous function over this. All right, but we're not going to say such that this is equal to 0, because that's what we're trying to check. Then we say then, so the idea here, guys, for this one, for taking the 0 vector, you let this first function, then you let this one, don't define it with using this thing, right? You just define the first part. Then after defining the first part, you're going to add them. You add f element of this continuous function plus a element of this continuous function, such that this is going to be this. We know, without even saying such that, say such that this will be the integral from AB f of x dx plus the integral AB e of x dx. And this implies that, now if you check this, let me say integral AB f of x dx plus integral AB e of x dx will be equals, it must be equals to the first function, right, to show that this is a 0 vector dx, right? And then this implies that we know that this is 0, right? This is equals to 0 AB e of x dx, which this is also equals to 0, which this implies that the integral of e of x dx is equals to 0 also. So since this is the case, this we can say therefore this A will be an element of W, and since this is an element of W, it means that thus 0 vector holds. As long as we got that this is equal to 0, its integral will be equal to 0. That means that the 0 vector holds. You see, right? Now, from here, we can check the scalar multiplication. I think the scalar multiplication is just going to be simple. We are going to say this. Let me take a charge. So from here, we're going to let F element of C A B. So remember this, I took it from the original question, right? What I'm letting here, F of X dx is equal to 0. So let me go back to that question again so that you don't get lost, right? So I took it from here. So I'm just letting this, right? So I've easily let F be an element of W before. So now I can just continue working with this, right? But if you want also, you can still continue with that structure of saying let F first be an element of W. You see, right? And C be any scale. And then we know that CF element of this will have such that the integral of AB f of x dx is equal to, we don't know if it's 0 yet. I have C here. We don't know if it's 0 yet, but we must prove that it's 0, right? Then this implies that I can take the C outside, f of x dx. This is C times 0, which is 0. And this shows us that thus CF belongs to W also. And hence we know that these things, since they all hold, we can deduce that this is a vector space or subspace, right? And therefore W is a subspace. I think it's of V. Yeah. Any question on this one? It's a subspace of V, right? So I'm sure you guys were able to write this one, if I'm not mistaken. If not, it means that now you'll know how to write it, right? So let me add this again here. Now when we come to question 2, they ask us what is a basis of a vector space. We can tell us what is the basis of a vector space. What is a basis of a vector space? They want a definition. So the simplest way to give a definition to this, again, we know that we know what is how to prove that something is a basis, right? So you can just come and say that a basis of a vector space, is a set of vectors. You see, and those vectors should satisfy that satisfy, you can, let's say, it satisfies the following properties. Here they just want to see you understand. When they ask you a question, most of the times you're allowed to freestyle, right? As long as you give the correct meaning of what you're saying. So the first thing, it must satisfy linear independence. Then secondly, it must satisfy spanning. You say, right? So we say that a basis of a vector space is a set of vectors. It's a set of vectors that satisfies the following properties: linear independence. Yeah. Why am I skipping things? Independence. I think some things I just write them in my mind. Then a spanning set. Here you can just say spanning because here you have already specified spanning set, but a set doesn't matter. So you can just also define it in this way: a basis of vector space is a set of vectors that satisfies the following properties: linear independence and spanning. Right? Now we come to 2.2. With 2.2, they say that we should, for what values of lambda is the set, the basis of R3. So this one is 7 marks. The best way to solve this is if you use a determinant, right? So you can use a determinant. You can do this. You can say question 2. Now you come and say, oh, I've already said question 2. Oh, what's wrong with my life? We can say 2.2. Then what you're going to do here, they already said for what lambda or for what values of lambda. So you need to pick some element, like you're proving a spanning set. You need to let, that's why here they asked you about the basis, right? You let A, B, C be an element of R3 such that you now equate this as a linear combination of this. We can say X, Y, Z, everything that is inside there, plus Y, this is 1 lambda 2 plus Z 1 2 lambda. And then this will just be A, B, C plus lambda plus X lambda. Actually, let me just do this. X lambda X 2X plus Y lambda 2Y plus Z 2Z Z lambda. And then A, B, C is equal to X lambda plus Y plus Z X plus Y lambda plus 2Z, and then 2X plus 2Y plus Z lambda. And then here we get that A, when I write the equations, A is equal to lambda X plus Y plus Z, and B is equal to, so this is going to be equal to X plus y lambda plus 2z, and then c is equals to 2x plus 2y plus z lambda. Then from here you write the equation. This will be lambda 1 1. Then was the other one not 2? Oh, this was, let me see. Oh yeah, the last x was 2 1 1. Yeah, it's fine. The 1, yeah, this one was 2. Then this is lambda, this is 2, this is 2, this is lambda, right? And then we have x, y, z, which is equals to a, b, c. We just wrote this in the form of a, b, x. Ax is equals to b. This is the form of ax equals to b. You say, right? Then now I take the determinant of a. We have to remember the determinant must not be equal to 0 for this to be a basis. And they're looking for those values of lambda that this is going to be a basis. So we're just going to do this. So we're going to have this lambda 1 2 1 lambda 2. You can use any method, right, of determinant. It's up to you. You multiply this, multiply this, multiply this. It's going to be lambda 3 plus 4 plus 2 minus lambda 2 lambda minus 4 lambda minus lambda. And this is going to be equals to, it's going to be equals to lambda 3 minus lambda minus this minus 6 minus 7 lambda plus 6, right? And then this will be, I think first we need to find one lambda. What values what values can you get from here? What values do you think we can get from here? If we plug 1 here, 1 will get 1 minus 7, right, which is minus 6. Then I think 1 will work, minus 1. Then from there we're going to use long division. You can use long division for that. Let's try and see. This lambda 3 minus, it doesn't matter how you do your methods, right? You can do them anyhow. Here we have lambda minus 1. So lambda 3 divided by lambda, we get lambda squared. And then this times this will give us 3 minus lambda squared. Then lambda to the 3 minus lambda 3 is 0. Then here we get lambda squared minus 7 lambda plus 6. We just drop these two because there's nothing we can subtract them with. And then from here, take this lambda squared divided by lambda, I get plus lambda. Then I multiply back, I get lambda squared minus lambda. Then now I know that this is minus 7 plus lambda, it's minus 6 lambda plus 6. Then when I divide this, I'll get minus 6 lambda squared plus lambda minus 6. Let's multiply back. minus 6 times lambda, we get minus 6 lambda. Minus 6 times minus 1, we get plus. And then it's 0 at the end. Then this one we can factor it out. Lambda minus 1 plus 3 lambda minus 2. Yeah, because if we add these two, we'll get positive 1. So this means that we must let this determinant to not be equal to 0 for us to get that answer. So we know that this won't be equal to 1, lambda won't be equal to 2, lambda must not be equal to minus 3. So this is what we have. This is the answer that they're looking for, the lambdas that we must get. Any question? The question was saying, for what values of lambda is the set S, which is the basis of R3? Then we found that. So we have no other question, right? So I'm gonna just skip to 2 points. Yes?
Yes. Or after finding our lambdas.
Yes? Are you there?
Yeah.
The one was asking, I think I didn't hear anything. I just heard after finding our lambda. He didn't say anything after that. Alright, we're just gonna go to question 3, right? Now, with question 3, they say this. They say that give the definition of a kernel of a linear transformation T. We can give us a definition of a kernel. A definition of a kernel. They say they want the definition of a kernel of a linear transformation T. Okay, so they say give the definition of a kernel of a linear transformation T. 2 marks, right? Now, for us to define that, let's just go to question 3 first. For us to define a kernel, so we're going to say that since we know that the kernel, this is what we know. And maybe let me start by writing this. The kernel, if we have T from V to W, then we know that the kernel of T will be equal to, first pick V to be an element of capital V, such that TV is equal to 0. So we can interpret this in ways, right? This is the kernel of a linear transformation T of a linear transformation we can say this transformation is from V to W. You say right now, you can say that is defined, then we're going to explain what do we mean inside there. It's defined as the set of V there. This small v represents all vectors in V, of all vectors V in V such that T V is equal to 0. And remember, this 0 is coming from the domain, right? You're the code domain. So we can specify where 0 is the 0 vector. In W. You see, right? So that is 0 is coming from the codomain. So we get that. Or you can specify here, or you come here and just say W. Then you don't have to say all these. You see, right? Then now you're also allowed to write whatever I've written there here. The kernel of T is equal to V element of V such that TV also 0 double O. You see? Do you agree here? Now, from here we have 3.2. 3.2, they say we should consider the following map T from P2 to R3 defined by this. So this is what you're going to do here. They said it's 6 marks, and then they said determine if T is a linear transformation. So looking at the 6 marks, you have to decide, do you think this can be a linear transformation? Yes or no? Who can tell me? Do you think this can be a linear transformation? And how many things are we supposed to check from a linear transformation? How many things are we supposed to check from a linear transformation? Two, right? So we're supposed to check 2 things. Let's say this is not a linear transformation. How many are we going to check? Let's assume this was not a linear transformation. How many things are we going to check if this was not a linear transformation?
2.
If it was not a linear transformation, we're going to check 2. Check. Okay, let me write this down here. For T to be a linear transformation, it must satisfy, let's say we must have T of A, B, A plus B should be equal to T of A plus T of B. Then T of C, A should be equal to C, T of A. So for this to be a linear transformation, these 2 must hold. You agree, right? Ne? Then for this not to be a linear transformation, they should hold, both of them. Let's say we don't want it to be a linear transformation. Are they going to hold, both of them?
No.
No. So it means that for us to check that this is not a linear transformation, we are only going to check one thing. You agree, right? That we are sure of that this won't be a linear transformation if we check it. Do you agree with me there? And this won't be 6 marks. If this is not a linear transformation, sometimes you need to look at the marks. Then you inspect, can this be a linear transformation? Let's say this. For an example, if I come and let F be 0, it means that this is 0, this is 0, this is 0. A, B, C are 0, right? If A is 0, B is 0, A, B, C are all zeros, it means that T of 0 is also 0. This is going to hold. Whenever you check with a 0, if you plug a 0 inside, then you find that you get a 0 at the end. This tells you that the addition 1 holds. So there's no need for you to do this one. It means that we're going to start with this. You see, right? Then if this holds, that's when you can go back here. That's when you can go back here and check. But in most cases, if this is the case, you're supposed to start here because this might not hold. It happens. If this was not a linear transformation, this won't hold. You see, right? Or it might, but one of them must not hold. So what you're going to do always, you're going to plug 0 inside. Everything that is inside T, you're going to give it 0. So you come and plug here. So if you get 0 at the end here, it means that the addition 1 will hold. Don't start with it. It's going to waste your time. If this was not a linear transformation, it was going to waste your time. So we won't start with it. We'll start with the other ones. So we'll start with the one of a scale. We'll start with this one of a scale. So we are going to say here they say it's 3 point. Let me just write it. You'll understand what I'm saying, right? So first we must let f be an element. Let me write the question here so you can see what I'll be doing. Remember, they gave us this question. They said t from P2 up until R3 defined by, this was defined by t of f, t of a plus bx. This tells us that f is equal to this cx squared, which this is equal to 2a minus b, a plus b minus 3c, c minus a. So what you have to do first, you must let this be an element of P2. You're going to let two of them. We let fg be an element of P2 such that you let it be an element of the domain, right? Such that f, we know that it's equal to a plus bx plus cx squared. So for us to edit this and make it look real, we can just decide to say, instead of f, we say f of x, and instead of g, we say g of x, so that it can make sense to us. We can have something that makes sense, right? F of x and g of x is equal to a1 plus b1x plus c1x squared. Then it means that we're going to add them now. F of x plus g of x is equal to, we can start by adding them if you want, but if you don't want to add them, you can come and add them inside. If you don't want to add them outside, you can come and check the transformation of f of x plus g of x. So this is equal to, you add them inside, just add them inside. This is a plus bx cx squared. You see, you can still add them inside if you don't want to add them outside. And this is going to be equal to a plus a1 plus b plus b1 x c plus c1 x squared. And this is equal to, according to that question, they say that at the end it's 2a minus b, meaning that a will be replaced by this. It's 2a minus b, so b will be replaced by this. And then second one is a plus b minus 3c. A plus b minus 3c. So the last one is c minus a. It's c minus a. Then we can separate this at the end. It's 2a minus b, a plus b minus 3c, c minus a plus 2a1 minus b1, a1 plus b1 is 3c1. I'm sure you can say, just take the ones that are of the same type, right? Put them together. These two, they go together. So I'm just gonna put them here. And you see that this satisfies the condition to say that this is t of f plus t of g. Since here we said f of x, we can just put it like that. This t of a plus bx cx squared t a1 b1x plus c1 x squared. So this is the same thing as t of f of x plus T of G of X. You see, right? The left hand side is equal to the right hand side. So I just started with this, but if you plug and find that, if I plug 0, you find that this is 0, you can start with the scalar multiplication. But since I already know that this is a linear transformation, I looked at the marks, 6 marks. Obviously, it has to be a linear transformation. In most cases, you can just inspect by the marks, by the mark allocation to say, no man, this is a linear transformation. So now let's check the one of a scale. Let f of x be an element of P2 such that f of x is equal to a plus bx cx squared, and let c be any scalar. Then we're going to have t of c f of x. This is going to be equal to t, then we plug what we know here, a plus bx plus cx squared. No, let me not let's see k, because I already have c inside. Okay. And then this is going to be equal to t ka plus kbx plus kcx squared. And this means that, remember, first we had 2a, right? So it means that this is just going to be 2ka plus 2a minus b minus kb. Then it was a plus b minus 3c. Ka plus kb minus 3kc. Then here was c minus a. Ka. And this is just going to be equal to, we factor out k. Can just factor out k. 2a minus b, a plus b minus 3c, c minus a. Then this is going to be k, t of a plus bx plus cx squared, which this is k, t of f of x. You said right, also this one holds. So since they both hold already, I think question 1 was like 13 marks, question 2 14 marks, right? Question 3 15. Already you know that you have 30. Yeah, you have like 40 something marks, right? 42. So if this holds, then you can now come and deduce to say that it follows that t of f of x plus g of x is equal to t of f of x plus t of g of x, and also t of k f of x is equal to k t of f of x. Hence, T is a linear transformation. You see, right? Then you are done with this question. Yeah, so I think we've already spent an hour. I think we can stop on this one, right? And then I'll give you guys to digest this. Then you can try to do other questions based on this. Then you consult. Then means that tomorrow we will proceed with 3.3. Then we go to question 4. Then I think we have around 7 questions. Yeah. Any question here?